Hi everyone and welcome to this new class in engine propulsion. Specifically we will discuss with greater detail turbojets and turbofans. So we discussed in previous classes the difference or the main differences between turbojet, turbofan and turbopropellers. So turbojets, basically they get some kind of air, okay, the exterior air. They get it from the exterior, they compress it. After that, the temperature is also increased on the combustion chamber. Then all of this energy is transformed in the turbine to velocity, and finally with a nozzle we get a higher velocity, okay, which compared to the initial velocity will give a certain amount of thrust to the engine. This is how a turbojet mainly works. Turbofan, the difference of the turbofan and the turbojet is that instead of having only one flow, we will have two kinds of flows. First, we will have something very similar to the turbojet in the interior, but we also have some kind of flow on the exterior, like this, which will actually be named as cold flow. Okay, so this will be hot flow, because the exhaust is at hot temperature, whereas this will be named the cold flow. The idea is that we have greater efficiency at subsonic flight due to a fan. And finally we have a turbopropeller, which instead of generating thrust due to the difference in velocity on the exhaust and the inlet, we will actually have the creation of thrust due to the movement of the compressor and turbine, and therefore the shaft, and that, given a gearbox, will be transformed into propeller kinetic energy. So this means a velocity, a given specific velocity for the propeller, will actually be able to generate some thrust. Now, to get more into detail and to just, get into all the topics, and for you to get to know exactly how these work, we will make a bit of a greater discussion, okay? Some more detailed discussion. So, as I mentioned, jet engines, turbojets, work based only on one flow. And this flow is initially called at low pressure. Now, pressure will be increased at the compressor in several stages, as we saw in the part of compressor. What we will have is an axial compressor with different stages, and these different stages will actually improve or increase the pressure per step. Alright, so in the combustion chamber we will get actually a very high pressure fluid. The combustion chamber will heat the flow to a high temperature, so not only will we have a high pressure fluid, but actually a very high temperature and high pressure fluid. Then the turbine over here will accelerate the flow by expanding it. And this means that the turbine will actually decrease the pressure and therefore accelerate the flow, and we will have the flow at higher acceleration, at higher velocity, okay, and at high temperature. So the flow, you can imagine at this point, has energetically speaking, has great conditions, okay? In this case, it will have the conditions of the flow will be greater than those in the initial conditions, so the velocity will actually be very much higher than the velocity in the inlet, and this will provide the thrust. Also, it's interesting to remember that the compressor is moved by the turbine. So when the turbine starts to operate, it will translate the movement with the shaft to the compressor, and the compressor will start compressing, okay, or pressurizing the flow to the combustion chamber in order to optimize the whole engine cycle. Finally, flow is further accelerated by the nozzle, okay, due to the geometric conditions of the nozzle, and we actually can use also an additional afterburner, right, as we discussed in previous classes. So the idea is that the final flow is hot, okay, it will have quite a high temperature and will become also low pressure. So this flow is basically optimized in order to be at high velocity. Now turbofans, and the main difference between turbofan and turbojet is that we have two flows, named hot and cold. The hot flow is basically the same or very similar, or the configuration of the internal part of the engine is very similar to the turbojet. However, in this case we have a high pressure turbine, okay, this one over here, a high pressure compressor, a low pressure compressor, and a low pressure turbine. Okay, and you may ask why. Well, the idea is that the high pressure turbine will actually move the high pressure compressor. So you know that the turbine will actually move, and because of the movement of the turbine we actually are able to move the compressor. So high pressure turbine will move high pressure compressor, and apart from that the low pressure turbine, okay, so just as a reminder, you know that the pressure at this point is relatively low, then it increases and it continues to increase. So this is why this is the high pressure compressor, and this is why this is the low pressure compressor, okay, because the flow at this point is at lower pressure conditions. Now, as I was mentioning, that low pressure turbine, so this part over here, the exterior part, okay, will actually move the low pressure compressor and also the fan. Now, what's interesting of this, and the main difference between the turbofan and the turbojet, is that we have the separation of high pressure elements, okay, and low pressure elements. And this is interesting because we have a low pressure turbine, we are able to move also the fan. And this fan, what we'll do is create or induce to the flow, to the cold flow on the exterior, some kinetic energy due to the movement of the fan. And this will be transferred in the end as an increase of the velocity. Not a lot of increase, but just substantial, a bit of increase. And as you know, the thrust is just the product of the mass flow times the velocity, or the difference of velocity between the nozzle and the inlet. So if we have a lot of mass around the cold, okay, so a lot of cold mass, a lot of cold flow, which means a lot of mass flow, but with little difference in velocity, that's enough to cover a lot of thrust, okay, just because we have a lot of the mass flow. So even if the difference in velocity is not that high, the fact that we're moving with this compressor, we are able to move all of this flow, will actually make the engine a bit more efficient. And this is just the idea of the turbofan. So turbofans are a bit more efficient in terms of subsonic flight because we also count with a fan. Okay, and this fan will generate a bit more velocity to the mass flow, and because there's a lot of mass flow, this will be converted to an extra part of a thrust. Okay, so overall thrust can be higher due to high mass flow, right? So combining the hot flow and also the cold flow, as we mentioned. Now, efficiencies in these cases in turbofans are higher than turbojets for subsonic flight. There's actually a mathematical derivation that at very high hypersonic speeds, actually turbojets work better than turbofans. So this is why you won't see turbofans for supersonic aircraft. It usually is turbojets because of the efficiencies. Okay, it's simply more efficient in subsonic flight, and in case of the supersonic flight, a turbojet will be more efficient. So what else? Here you have some examples of what turbojet engines look like. So I would like you to check and be able to determine the different elements on this one. For instance, this one is this engine, you can only see the exterior, so it's not that obvious, the different elements, but you can see all the connections, all the thermodynamic connections and electric connections, okay, that are required in order to fulfill all of the characteristics, that all of the potential, okay, that this engine can give. So you can see different elements some refrigerants, some, you know, just different elements of the engine, which are quite interesting, to be honest, and which can be, you know, it can be of your interest to determine the different elements. However, in this course I will just focus on the different concepts, okay, that we can see over here. So first of all, you see the inlet on this part. You see the different compressor stages, okay. You can also determine that these ones are a bit different than the following ones. In fact, you can see that the airfoils in these cases are quite larger compared to the latter cases, and this is because the pressure in this in this stage of the aircraft, or sorry, of the engine, is actually lower than in these cases. This is high pressure conditions. So due to the difference in pressure, we will need some characterization or some other of the airfoils, okay, that compose the compressor. So this is actually quite interesting to note. All of this will be the compressor stages, okay, and you have the inlet, as I mentioned. This is the shaft, and in this case you can see that the combustion chamber is actually radial, is on the outside, due to the fact that the flow will move in this direction, and it will be introduced in this point with the combustion chamber. And as you know, the combustion chamber will increase the temperature, and after that you can see that the combustion chamber will move the flow towards the end, towards the turbine. The turbine will expand the flow, so it will decrease the pressure and therefore create a higher velocity, right? And after that you just have the exhaust, you have the nozzle, alright? So this would be a typical configuration of a turbojet. I wanted you to see a real case, okay, so that you can analyze the different elements if you are interested in that. Now, turbojet examples are mostly, as I mentioned, supersonic flight. You can see this one in this case. You can see it has afterburners, all right, with you know, it looks like fire is coming out. In fact, you can also see the different all of this. You can see that there's this continuous kind of burning. Can you see that? That is related to the velocity at which the speed at which the fluid is coming out from the engine itself, and you can see that it is supersonic. Okay, the speed of this fluid is supersonic because we have kind of shock waves, and these are little shock waves, okay, that will appear at different at different time rates due to the velocity, the exhaust velocity of the engine. So if you see some, if you see this kind of element, you can determine it is related to shock waves. So you can actually determine the velocity at which the speed at which the speed at which the flow is actually coming out due to analysis of this flow. All right. So this is the first example. This is the Blackbird from NASA. This is it's quite interesting to note. Okay, I like this photograph because you can see that there's also more technology going on in the nozzle. Okay, depending on the amount of thrust that you need, you can actually close. I'm not sure if it's very visible, but you can see that this is closer. Okay, this surface is a bit smaller than this one over here. So you can actually have a difference in the amount of thrust that one motor or one engine is given with respect to the other, which may serve for some kind of mechanics, some kind of rigid body mechanics. It can be useful to orient the spacecraft in one way or another. Okay, and it just means that the nozzle can perform, and probably will automatically perform, in the best optimal way. Okay, so you can imagine that there's a lot of computers going on here, okay, in order to optimize how this is closed, so how the nozzle is actually focusing the fluid going out of the aircraft. Okay, so it's quite interesting to note this technology is actually it is being developed, and it is quite useful, to be honest, in order to optimize the amount of thrust given by an engine. And this one I like also. You can see that I'm not sure if it's very visible, but this is the main axis, okay, of the engine. But you can also see that there's a change of the axis on this part over here. It's kind of looking downwards, isn't it? And this is usually known as thruster vectoring. What it means is that you can actually point the nozzle to one direction or another in order to get thrust in one direction or another. And this can be also used in order to orient your aircraft in some specific way or another. So if you need to make a quick rotation of the aircraft, a quick maneuver, you can actually, and probably automatically, the whole computers in the aircraft will be capable of orienting the fluid in one specific direction in order to get an impulse by Newton's third law, okay, by reaction, in the opposite direction. So this is how complex, okay, some of these engines can actually get, and this is the technology we're actually looking for, right? Also, I wanted to include some turbofan examples. Turbofan, I'm sure you're probably more familiar with. If you ever flown with an aircraft, with a commercial aircraft, you have almost for sure seen one of these turbofan engines, okay? You just get to see the exterior, but this is all the interior. It's quite interesting to note that this is the fan, alright, and you get all the different compressor stages, and also, you know, the shaft, and yeah, it's difficult to note, but there's a combustion chamber here, okay, due to the high pressure. You get here the combustion chamber, and then it is expanded with the turbine, and therefore you're actually able to transform the low pressure to velocity, and actually accelerate the fluid, as we mentioned before. This is quite similar to the turbojet, and it is also interesting to note all of this space, okay, all of this part over here, which will be covered afterwards with with some kind of mechanical element. And what we'll do is actually have a cold flow, right, around the engine. So you have the combination of both, and this is the idea for turbofan. This is the dimensions of I'm not sure which model this is. I think it's the model for the 787, and this engine is quite efficient. So you can just see the different elements, as we saw the fan. In this case, this is covered, okay, and this is the exterior. You can also see all the refrigeration, different elements, key points, electronic connections, all of that of the turbofan itself. And finally, this would be the example of what you would see on a turbofan. You just get to see the external cover, okay, and the fan usually. So for a turbofan, you will see the fan and the cover. That's all. But you must know that the interior is what we described before. Okay, so the interior of the engine is actually like this. And one thing to I like this photo because, apart from the dimensions, okay, which is quite interesting to compare with a person who was walking bound, it's quite interesting to note that you can determine the cold flow, okay, where it will go, because there's actually you can see it's void. There's no structure in this part. You can see the fan, but in this part over here, you can see that the fan is actually empty on the posterior. So you get the fan and you get the cold flow flowing, and that's all. And also you get the hot flow on the middle, okay, in order to generate the maximum thrust. So, well, it's a combination of both, right? It's like a turbojet on this part, and you actually have also the fan, and the fan will move the cold flow on the surroundings. So this is all right? If you want to know also this, you may be interested in knowing why this is used. They usually use this in order to recognize if an engine is working or not. It's kind of imagine that you're a long distance from an aircraft and you don't know if that aircraft is moving or not. while moving if the engine is operating. So you can easily know that if the engine is operating just by seeing if this element in the center is actually moving or not, and therefore you can see if the engine is operating or not. This can be useful for control purposes from the tower station or whatever. Okay, so I think this is all. As always, if you have any questions, let me know. And in addition to that, I try to put a lot of effort into getting the most material. I would appreciate it if you feel like this content is good and useful for you. I would appreciate it, a good review on your part, and I'm willing to listen to all your petitions. Okay, and I would like to provide the best material for you. So just let me know if you have any questions, if you have any doubts. Let me know, and I'll try to look for a solution for those. Okay. So let's go to the next class.